Hello all and welcome back. So in this video, let us now move forward and try to find out what is the complexity of different operations which we have done in our BST class. So in the last couple of videos, we have implemented the methods such as insert, search and delete in our BST class, which we saw are the major methods or operation which we have to perform, right? So in the visualization as well, different visualization which we saw, there were these three methods available, right? Because these are the only three methods which you mainly are required to do. Along with that, of course, there can be traverse, checking if it is BST, but that is something which we have already done. Now, coming to these main operations, okay, so let us take them one by one. Let's say first one is search. Now, for search, let us assume that our tree is something like this. Okay, so let me copy this node and let us make multiple nodes. Say I'm getting my tree, which is almost maybe I would say balanced, right? So not taking a degenerate tree overall. Let's say this is my tree. Let me just connect the notes real quick. Also, everyone, please make sure that you download these notes. They will be very much helpful to you in revising and before any interview as well. Great. Now, if my tree is not skewed and say I'm getting a tree like this, what used to happen exactly? We used to go to a node. Based on the value of the root, we used to take a decision whether to go right or to go left. Then we used to go to say right, then to this position. Overall, to do all this thing, right? To do all this different steps, I am effectively traversing OH, where H is my height. I am not going to each and every node. Okay, so height of tree. It is in order of the height, whatever is the height. In binary trees, we used to go to each and every node to, let's say, search for a particular node or value which I'm finding, right? Here, that is not the case because I am going one either on the left side or on the right side. That will effectively come out to be what is the height of my tree. Now, in case if it is skewed, then we know how the height is n, right? If it is not skewed, then we majorly have seen that height will be equal to log n, right? So around log n is where height is. For the tree where I have this particular skewed tree, we know that it is not a desirable tree, right? It is as good as a linked list. And we know in searching in a linked list, the overall complexity is O of n only. Great. So that is with respect to search. Now let us see for insert. Similarly, for insert, okay, so if I just scroll down a little bit and let me copy this particular tree as well, maybe we can use the same one only. Now for insert, actually the whole process is exactly same, right? So I go to the root, then I see where I have to insert. Let's say I go right, then on the left, let's say it's saying go to the left, and I'm inserting the node here. Okay. So the whole process again is very much similar. So the complexity becomes again big O of h, right? Where h again is the height of my tree. Now, in a very good case, in a case of perfect binary search tree, it will be log n. In a tree which is skewed, it will be O of n, right? But majorly, in major cases, if we are making a tree, right, not a linked list, we will try that our tree is going towards where it is balanced, right, where the height of each side is not a lot high, like there is no much difference. So normally we say that we are able to do things in O log n time, which we know is a very good advantage over O of n. So O log n is very good as compared to O of n, something which we have seen, right? When we compared binary search with a linear search. Great. So pretty sure that these will be clear. Now let us move forward and talk about delete. So third operation is delete, which of course was a little bit tricky, but let us see that one by one, everyone. So again, I will be just copying this tree only. It is a good tree to work on. And maybe we will add some nodes here. Great. So this is a tree, let's say, which we have everyone. Now, what I'm doing is I am adding, say, another node here. And even let's say one more should be fine. Okay, great. So now pay attention what exactly is going to happen. Let's say I want to delete this particular root. Okay, let's say I want to delete root only. Now what's going to happen? For deleting root, or let's say any other, if let's say even I want to delete this particular node, the first operation is, the very first part is going to that node, going or finding node we want to delete. Let's say we find it at h1 height. Okay, so let's say this is at h1 height. What effectively I'm saying, let's say if you want to delete this particular node, let's say you find it at h1 height. Now your node can be something this as well, if it is a very big tree, okay, when many elements are there. But let's say we are able to find it at h1 height. Great. If we have to delete this, then what's the second work we do? Find replacement. Find replacement. For replacement, let's say we find the replacement at some h2 height. Okay, so what I effectively mean, everyone? Let's say this is my overall tree where I find h1, and say I'm changing it with this particular node. Okay, so I'm changing it with this node. Maybe we can take the example, or say for this particular node, we are, one second, it's not the vanishing pen, so should be fine. Yeah. For this particular node, let's say I will be finding this at h2. Okay. You will see one thing for sure, that h1 plus h2. Okay. In case it can be equal to h, right? It will not be greater than h, because some point you have find the node which you want to delete, and based on that you are now finding the replacement. The last work used to be delete the replacement. Now in deleting the replacement, we will not be making another call. The reason is that replacement, for sure, left or right is going to be null. So it will also be in h2 level. So what I effectively mean by that, let's say you have to find a replacement for this node. You will go here and keep on going left until this is none. Now if this is none, and let's say it has a right subtree, we are just going to make this as my new node here, right? So we will just correct this connection here. This is something which we discussed. It will not be making a call again, because we know that one side of this replacement is going to be none. So at h2 overall, we will be able to work this out. Okay, so let me just explain it a little bit again. Let's say at some height, you have to delete your tree, that is h1. Okay, you find the node at h1. Then at some height, you will find that, okay, what you can replace it with. So that, let's say, is h2. Along with this, we will have to make sure that we delete the replacement as well. So this will also be h2. Now your replacement, because it will have, of course, one of the side none, either the left or the right. Okay, because that is the condition on which we find replacement. For getting the min node, we used to keep on going left until the left is not none. Right, everyone? So if in a way we just see that visually, it will always be less than 2h. Right? It will always be less than 2h, because this is, let's say, h in worst case, it is proper h, and then h2 will be some part of my height. So what I can say, pay attention everyone, h1 plus h2 plus h2, it will be less than 2h, right? If that's the case, now I hope all of you remember n to n, the complexity overall still gets to big O of h, right? So if I'm able to get a very good balanced tree out, right? If I'm able to get a very good balanced tree, okay, and I'm not talking about these trees, the skewed one, because again, we know that the skewed one, they are not the ideal tree which we want. So if this is the tree, then it's a problem. So for a balanced tree, we are able to see that all these operations can be performed in big O of log n time, right? Because the height is around log n, we can say that if a tree is balanced. And the balanced tree we already know, where the left and the right subtree have a height difference which is less than or equal to 1. Okay. So this is the complexity. Let me write that down as well. This is the major conclusion. For a balanced BST, which is the overall tree which we want, all operations are big O of log n. Now comparing that to, let's say, in list or an array, if we have a sorted list or an array, right? Because the nodes are continuous one after another, not the nodes, the values. There we have to do the shifting, right? Where there we have to make the space. If we are deleting, then also we have to do the shifting. So all that actually makes used to make the complexity big O of n. Just by using trees and making sure that they are balanced, we are able to increase that complexity overall to a level which is big O of log n. And we know that how good of a overall improvement that is. Okay. Again, that will depend a lot on the tree structure, but we make sure that when we are making the tree, we are keeping it balanced. So there are different ways or different trees which are defined for this particular overall aim as well, that we want that our tree should remain balanced. Okay. So which we are gonna just touch upon in the next video. But the basic idea is that by using T properly, I can have things, all these operations in big O of log n from big O of n, which again is a very, very good improvement which we have made. So I'm pretty sure now all the operations, how exactly they are doing, okay, it is fine. If someone asks you about the overall complexity, you should always say big O of h, not big O of log n. But yes, for a balanced BST, it is big O of log n, like of the order big O of log n. Okay. So cool, everyone. I'm pretty sure that the complexity part will be clear. Now let's meet in the next video where we will see some ways or touch upon some ways this is actually handled.